Most software and network engineers use the internet every single day without truly understanding how their data is physically carried. At the heart of this system lies Layer 4, the transport layer, where data is prepared for transit, and you must choose your specific carrier. The two primary options ruling this space are TCP and UDP, operating on completely opposite missions. One prioritizes absolute data security and integrity, while the other sacrifices everything for pure speed. Choosing between them dictates exactly how your web apps, video streams, and databases perform. In this video, we will break down the hidden mechanics of both protocols, unpack port allocation, and see how packets avoid corruption so you know exactly when to deploy each option in production. Let's dive straight into the deep architecture with the secure handshake of TCP. TCP, or Transmission Control Protocol, is explicitly connection-oriented and guarantees reliable, error-free delivery. Before sending data, TCP establishes a formal connection via a mandatory three-way handshake. The sender issues a SYN packet, the receiver replies with a SYN ACK, and the sender confirms with an ACK. Once connected, ensuring that the arriving data blocks aren't corrupted during transit is vital. Inside the TCP header, a cryptographic checksum field allows the receiver to perform a mathematical validation. If the values mismatch, the data is flagged as corrupt and immediately dropped. To further secure the stream against injection attacks, the sequence numbers tracking these segments are generated entirely at random, rather than starting at 1. If a packet vanishes into a silent network, TCP relies on an internal retransmission timer triggered the moment a segment is dispatched. If the destination's ACK isn't received before this clock hits 0, the protocol assumes the worst, treats the packet as dead, and automatically retransmits it. To prevent network slowdowns from waiting on an ACK for every single block, the dynamic window size determines the maximum volume of bytes allowed on the wire before an explicit acknowledgement is mandatory. This window dynamically expands on high-quality paths to maximize throughput and shrinks defensively on unstable connections. When the communication finally concludes, TCP elegantly tears down the session using a precise 4-step closing process, exchanging FIN and ACK flags to ensure both parties safely close the gates. This incredible safety apparatus ensures your files never arrive corrupted, making it the perfect foundation for web browsing, emails, and file transfers. But all this tracking, timing, and handshaking introduces massive latency overhead. What happens when you don't care about a perfect file, but you desperately need real-time speed? That brings us to Chapter 2. User Datagram Protocol, or UDP, takes the exact opposite approach to networking. It is completely connectionless and operates on a pure best-effort delivery model. If you scan the UDP header looking for complex error recovery tools, window sizes, or flow control mechanisms, you won't find a single one. They simply do not exist. UDP skips the three-way handshake entirely. It doesn't ask if the receiver is online or ready. It simply compiles its protocol data unit, termed a datagram, and immediately fires it into the wild network. If a datagram gets obliterated by an overloaded router midway, it's gone forever. There are no sequence numbers to rebuild order at the destination, and no tracking timers. Now, you might think, why would any sane engineer use a protocol that deliberately drops data without an eye blink? Because it is blindingly fast. For applications like live video streaming, voice over IP, VoIP, online gaming, and rapid DNS queries, minor packet loss is completely unnoticeable. Losing a single microfragment of an audio wave or a video frame is vastly better than pausing the entire live broadcast for seconds just to wait for an ancient TCP retransmission. UDP strips away all structural fat to achieve raw performance. Now that you've fully grasped the ideological split between reliable connection streams and raw datagram bursts, a critical structural question remains. When these packets land on a server hosting dozens of different applications, how does the operating system know exactly where to send them? Let's unlock Chapter 3, the gateway ports. Ports are numerical endpoints that act like specialized loading docks, allowing TCP or UDP to direct incoming data streams straight to the correct application process. On every single network-connected machine, the complete port number spectrum spans from 0 all the way to 65,535. This massive range is formally segmented. Ports ranging from 0 to 1023 are universally recognized as well-known ports. These are strictly managed and allocated by the Internet Assigned Numbers Authority, IANA, to power foundational system services. Depending on your application type, your data routes through these explicit doors. For reliable TCP operations, you will routinely find port 443 for encrypted web browsing via HTTPS, port 25 for executing outbound email routing via SMTP, port 110 for managing email retrieval via POP3, port 22 for secure remote terminal server management over SSH. Flip over to the UDP side where speed rules, and you encounter port 67, which dynamically automates network IP configurations via DHCP, port 69 for rapid, lightweight, unverified file delivery over TFTP. Interestingly, several critical Internet services operate as hybrids, leveraging both transport mechanisms depending on the specific operation. Large-scale file transfers deploy ports 20 and 21 for FTP. Old legacy terminal connections run on port 23 for Telnet. Network infrastructure monitors run on ports 161 and 162 for SNMP. And the backbone directory of the Internet maps directly to port 53 for DNS queries.
Understanding the ports and the protocol differences gives you a solid foundation. But to operate like a true systems architect, you must understand the hidden interactions that happen under the hood between layers and machines. Let's trace how these protocols communicate behind the scenes. It happens across two distinct vectors: adjacent layers on the same machine and peer layers across the network. First, consider adjacent layer interaction. On your local machine, layers work as a tight unit. When an application protocol like HTTP wants to push data, it calls directly down to the layer immediately beneath it, TCP, requesting a specific service, such as error-free delivery assurance. The transport layer accepts this raw application block and performs segmentation for TCP, or creates datagrams for UDP, wrapping them with an analytical header containing ports and a cryptographic checksum fields to catch internal data corruption. Second, look at same-layer interaction, often called the peer-to-peer network telephone. This is the direct logical conversation between machines. The transport layer on the sender machine uses header fields, like random sequence numbers or ACKs, to communicate exclusively with the transport layer on the receiving machine. They align, negotiate window adjustments, and handle reassembly coordinate parameters entirely in the background, independent of the routing path below them. But remember, if data arrives out of order due to dynamic network routing, only TCP takes the effort to meticulously resort those segments before exposing them to the application. UDP completely refuses to sort. It passes the raw jumbled packets straight up, leaving the final application to sort out the mess entirely on its own. To quickly recap what we've uncovered today, Layer 4 prepares data for transit and manages how it's handled across the network. TCP is connection-oriented, executing a three-way handshake, tracking segments with sequence numbers, and utilizing timers and window sizes to guarantee perfect data integrity. UDP is connectionless and unverified, discarding safety overhead to unlock maximum raw performance for real-time video, gaming, and VoIP. Ports range from 0 to 65,535, with the first 1,023 ports tightly managed by IANA for standard system services. Peer transport layers talk directly across the wire using protocol headers, shielding your application from dealing with packet fragmentation and corruption. If this deep dive helped you understand the transport layer, hit that subscribe button right now.